Bloody hell, it's been a while now since recording my former video. Well, Papa's back, biatch.
That's your robot? Yes, I got one. What does it do? Anything I want. Give me a juice box, biatch.
So, in today's topic, we are going to be doing electricity. It is said that the greatest invention in human history is that of anesthesia, an aphorism accredited to a guy named Sir James Young Simpson, who was a Scottish obstetrician. He was also the first to popularise the use of chloroform as an anaesthetic to put patients to sleep before surgery. Before this, patients would undergo surgery, oftentimes while still being awake, which often led to more blood lost and hence greater casualties. Well, to that end, I would also like to add that the second greatest invention in human history would be that of the electric circuit. The first electric circuit was invented by Alessandro Volta in the 1800s. During his experiments, Volta discovered that he could produce a steady flow of electricity using bowls of salt solution connected by metal strips. His discovery would then genesis the birth of high-speed railways, lasers, fusion and fission reactors capable of harnessing the power of the sun, and telescopes in space that could peer into the atmosphere of distant exoplanets. And whatever the hell this is.
Should I look for businesses by that name?
Joe, pickle me.
But they all have one thing that unifies them all, and that would be what courses through their veins of metal, their lifeline, their blood, which is electricity. This is electricity, and it is composed of three things. Number 1, electric current. Number 2, charge. Number 3, voltage, whereby electric current is the flow of charged particles in a circuit, aka electrons, with the formula of V is equal to IR, where V is the voltage, I is the current, and R is the resistance of the wire the electrons are flowing through. Now, charge. Charge is defined as a product of current and the time taken for the current to flow past the point, with the formula of Q is equal to IT, where Q is equal to charge, I is equal to the current, and T is equal to the time taken. Voltage. Voltage is defined as the work done per charge, having a formula of V is equal to work done over charge. These three formulas are going to be the backbone of this topic, and using them, you will be able to derive other kinds of formulas, such as work done or even power. But you can find the proofs and how to derive these equations in my worksheet, which can be found in the description of this video. Now, we can explore something called ohmic relationships, which states that for any ohmic conductor, the potential difference must be directly proportional to the current flowing across it. This allows us to study the many behaviors of conductors such as lamps, semiconductors found in your computer, and even LED light diodes. While the concept of a perfect ohmic conductor is a theoretical idea, real-world materials exhibit varying degrees of ohmic behavior depending on the conditions and the scale of the application. But if we were to create an ohmic conductor, its current to voltage graph would be a straight perfect line. Whilst a filament lamp would initially act as an ohmic conductor, it would gradually curve. This is because as the temperature inside the filament rises, the atoms in the wire gain kinetic energy and vibrate more vigorously. This increased thermal motion makes it more difficult for electrons to flow through the wire, resulting in a higher resistance, and therefore the curvature. Lastly, a semiconductor diode. This one is a unique case, but the magic trick is in the name. Semiconductor. Semiconductors are normally not conductive until a threshold voltage is reached. Essentially, it is the voltage required to allow a current, the flow of charged particles, to course through the semiconductor. Okay, so with that out of the way, we can now start working some past paper questions. And I will be starting with the February-March 2023. So let's get started. Define the potential difference across a component. The potential difference is the energy per unit charge, or the work done per unit charge. So I'm just going to write energy. Moving on to B. So we have a variation graph with V as the x-axis and I current as the y-axis, and we're supposed to answer some questions about resistance. So the way to answer these questions is to first try and understand the relationship in the graph using a formula. In this case, we are using V is equal to IR. And now we'll try to solve to get the y-axis and the x-axis. So I becomes the subject of formula because it is the y-axis. We need to make it become this form over here. Y is equal to mx plus c. In this case, you won't be having a c because there is no y-intercept. So I is equal to v 1 over r. I is your y-axis, v is your x-axis, and 1 over r is your m, or gradient. Now, the resistance of the diode, we have to determine the resistance of the diode in the range V is equal to 0 to V is equal to 0.25. 0.25 is going to be the midpoint between 0 and 0.5, so somewhere over here. 0.25. Right, so the reason why it is a straight line horizontal to the x-axis is because resistance is very high. So resistance is very high. Question 2. The variation, if any, in the resistance of the diode as V changes from V is equal to 0.75 to 1. 0.75 is going to be somewhere over here. Volts. So, as we can see, the graph seems to be climbing at a very steep pace. The reason why is because resistance is decreasing as voltage increases, and we can prove this also using the formula. So once again, V is equal to IR. I is inversely proportional to IR. V is proportional to I. Resistance decreases. This causes the current to increase, and as current increases, since V is proportional to I, when I increases, V also increases. So resistance decreases as V increases. Also, we can observe this in the graph. V is increasing and I is increasing, so they're both increasing, but R should decrease because of the formula. Okay, so moving on to the next question. So we have some circuit, a battery of 12 volts, and a current of 2.7 amperes. Right, so we need to calculate the current in the resistance wire. The resistance wire is between point X and point Y. So we are going to be using Kirchhoff's first law. There. So what Kirchhoff's first law states is that the current being produced by a battery is supposed to split when it reaches a junction. In this case, it's splitting at X to produce 1.5 amperes for the second wire, and we are to calculate how much amperes distributed to the resistance wire. And the way to do this is to take the main current, which is 2.7 amperes, minus 1.5, and that would be 1.2. Also, when the currents finally meet at junction Y, they should add up to produce 2.7 amperes once again. Okay. Part 2. Determine the resistance of the variable resistor. Okay. I'm just going to get rid of all this chunk. Okay. So we need to calculate the resistance of the variable resistor, which is RV. And we're going to do this by using V is equal to IR. And what are the things that we know? We know that V is equal to 12 volts, I is equal to 1.5 amperes, and R, well, R we have R total because we also have this 5 ohm resistor, so 5 plus RV. Okay, making R the subject of formula, V over I, 5 plus RV is equal to 12 over 1.5. RV is equal to 12 over 1.5 minus 5 is equal to 3.0. That's your resistance. Part 3. Okay, we need to calculate the potential difference between wire XZ and between X W. So we need to calculate the potential difference between, I'm just going to use a new color. I'll go for purple. So we need to calculate the potential difference between point Z and point W. That's pretty much what it's asking to do. Okay. And to do this, we are going to be using the formula V, which is potential difference, is equal to length 1 over length 2 times the EMF by the battery. This formula can also be done with resistors. This formula can also be done with resistors, so V is equal to R1 over R1 plus R2, also the total resistance, times the EMF from the battery. This helps us to calculate the potential difference at a particular point. So imagine we had two resistors here, 1 and 2, and we needed to calculate the potential difference at point Z. We would use this formula where this is R1 and this is R2. So V is equal to R1 over the total resistance times the EMF, and that will give you the voltage. Why? Because V is equal to the SI unit of resistance is ohm over total resistance is ohm plus ohm times the EMF, which has an SI unit of V, voltage. Ohm plus ohm gives you ohm. Keep in mind that ohm times ohm would not give you ohm, it would give you ohm square. So times V, these two ohms cancel out, and then you get the potential difference, which is V. Okay, so calculating the potential difference across point X and Z. V is equal to L1 over L2 times the EMF. We know that point length L1 is 1.6 over 2 meters times the EMF, which I believe was 12, yes, times 12. And that gives us 9.6 volts. I'm just going to erase all of this now. Okay. We also need to calculate the potential difference between point X and W, but we're not going to be using that formula now. We have a resistance over here, and we have the current. So, because of this, we can use V is equal to IR. So, for point XW, IR is equal to 1.5 times 5 ohms, which gives us 7.5 volts. Now, the potential difference between point X and W is simply the difference between the potential difference of both lengths. So PD is equal to 9.6 minus 7.5 is equal to 2.1 volts. That's your answer. Okay, so the resistance of the variable resistor is now increased. So the resistance of this variable resistor is increased, meaning the total resistance of this wire is increased, whilst the resistance of wire XY remains constant. I guess I'm just going to write constant like this. Okay, so by considering the currents, so I, in every part of the circuit, state and explain whether the total power produced by the battery decreases, increases, or stays the same. Okay, so the formula for power in electricity is P is equal to IV. We also know that V is equal to IR. We can make... Actually, we are working in terms of currents. So let's just replace this V with IR. P is equal to I square R. Great, now we have two equations for power. Okay. I'm just going to write V is equal to IR just in case we need it. Let's start by answering what will happen to the current that enters the variable resistor. Well, we know that I is inversely proportional to R. So, as resistance increases, the current decreases. So, that's your first point. Number one, the current in the variable resistor decreases as resistance Okay, so what's going to happen to the power? Power is proportional to I from this equation, and even using this equation is going to give you the same thing because current is decreasing, therefore power decreases. So number 2, power decreases the third point we can write about wire X, Y. The current in wire XY is going to remain constant as the resistance doesn't change, it remains constant. So current in wire XY remains constant. As resistance does not change. And those are your 3 points, and I do apologize for the horrible handwriting. I'm still getting used to this, I haven't done it in a while, so please forgive me. Okay, so question number 2. An LDR. Okay, so again, we have some circuit and we have an LDR attached to it as well as a resistor. So we need to calculate potential difference across the LDR using V is equal to IR. We know the potential difference and we know the total resistance, which is RT is equal to 1800 plus 1200 is equal to 3000 ohms, but we do not know I, so we need to calculate the current in the circuit. So I is equal to V over R is equal to 9 over 9, that's a horrible 9, over 3000, and that is going to be 0.003 amperes. Now we can use the current to find the specific potential difference across the LDR. So V is equal to IR is equal to 0.003 times 1800 is equal to 5.4 volts. Moving on to part B. Okay, we have a galvanometer. Galvanometer, what? I can't pronounce. Anyways, this device is meant to measure when the potential difference across two wires are equal. So when the potential difference at this point is equal to the potential difference at point Z, it will have a reading of 0. Let's move on to question number 1. Calculate the length XZ along the resistance wire. XZ. Okay, so because we know that the potential difference are supposed to be the same, we also know that the potential difference at point Z should be 5.4 because it's connected over here. So 5.4. So point Z, 5.4 volts. Okay, we can now use V is equal to L1 over L2 times the EMF, making L1 the subject of formula in a moment. We have V over E, L1 is equal to V over E times the total length. So that would be 5.4 over total, the EMF, which is 9, times the total length, which is 1.2 meters, is equal to 0.72 meters. So the last part of this question, the environmental conditions change causing a decrease in the resistance decreases of the LDR. The temperature of the LDR remains constant. Okay. The way an LDR functions is that when the amount of light striking the LDR increases, the resistance decreases. That's how an LDR works. So using this information, and I'm just going to write V is equal to IR for just good measures, state whether there's a decrease, increase, or no change to the intensity of light illuminating the LDR. If the resistance is decreasing, that means there's an increase in the intensity of light striking the LDR. So intensity increases. The total power produced by the battery, power is equal to IV. I'm going to substitute I, so we're going to get this. So V squared over R, power is inversely proportional to R. When resistance decreases, yes, okay, power increases. So power increases the length xz so that the galvanometer reads 0. Okay, using V is equal to IR once again, V is proportional to R. When R decreases, V decreases, so the voltage in this second wire over here is going to be low. And so that the galvanometer reads 0, we also need to decrease the wire over here so that this wire XY also has a low reading, or should I say low voltage or potential difference. So I hope that made sense. Length XZ decreases. Okay, that's all I have for today. I'd highly recommend going through the worksheet. You can find it in the description of this video. I have a bunch of past paper questions and the answers in there, including the notes, which I have spent a lot of time structuring so that it's as beautiful and coherent as possible for your exams. So I hope you find my worksheets helpful, and if you enjoyed the video, I'd highly appreciate dropping a like and subscribing. See you next time. Bye bye.